So last time we talked about linked list. We kind of finished up an implementation of linked list. And just to remind you, linked lists are these node structures. We did a doubly linked list where each node points to the node in front of it and behind it. And we looked at these different methods that are common to linked list, adding to the list at the end or at the beginning, searching through the linked list for a value, removing an element, searching from the end of the list to the front and from the front to the end. And I've posted example code on Canvas, which is partially the code we've been writing in class, but it's a complete version of it that's fully commented. So you can get that on Canvas. It is in the file section of the course, but it's also linked from the front page from the last lecture that we had. So just to show you, it's just these three files that we were working on. So the linked list header file, and pretty much all of these we implemented with the exception of the ones that move backwards instead of forward to back, which you can imagine is just switching a couple of lines of code. And so this is available for you on Canvas. There are a couple of added things. For example, just for convenience, this is a C++ feature that's kind of nice, overloading this operator like that you use for cout, so that you can just cout and give the list itself, and it will convert that and print it for you rather than having to call a method. But that's all available on Canvas, and everything is implemented there. I think one thing that we did not get to do in class that I will touch on briefly is this destructor function that's pretty important. So this is for the linked list itself. And all that this is doing is iterating through the list. You can see the while loop that we were using to iterate through the list to like print it and do things like that. And we're just taking each node and using that keyword delete on the node to get rid of that memory and free up that resource. One other note, so we had quite an interesting time with the null pointer keyword. You remember we had a compile error with that. So I did look into that a little bit to see what was going on, because if you remember, it was kind of strange. If we included the IOStream library, for some reason, it worked. And if we didn't, we got the compiler warning or error that null pointer is not defined. And so it turns out, and I've put it in comments here in case you're curious. So by default, I was just running a G++ command, which actually links to Clang on Mac, but what was important is I wasn't specifying the version of C++ that I wanted to use. And by default, on my operating system, it actually uses the C++ 1998 standard. So some of you probably weren't alive in 1998 for that. But that's what it defaults to. And in that standard, in that version, the null pointer keyword's not defined. So to fix that, you should specify which version you want to use. Again, it will work without it, but it'll just choose on its own. And in our case, that kind of caused us a problem with null pointer. Now, why did it work with IOStream being imported? So that's actually a little bit of a tricky thing with the way that, at least on this operating system that my compiler is configured, it kind of secretly does some switching around for you in the pre-processing step and goes in and kind of just find and replaces those null pointers, but only when the IOStream library was included. So it's somewhat a non-standard behavior. And so that's just kind of an interesting side note, which is kind of a thing that you deal with a lot in bigger, more established languages that have been around for a long time. But in summary, that's the reason why we ran into that error. And so if you run into similar problems, you kind of want to check these things and see. All right. So that code is available for you on Canvas. And as you look at it, if you have questions or if you find any bugs or anything in it, let me know, and we'll talk about it in class and fix it or whatever. It is based on the code that will be used for your challenge one. So that's kind of what guides like which methods and the return types and that stuff. So today we're going to move on from linked list, sort of, and we're going to move into stacks and queues. So how familiar are people worked with stacks and queues before? You know, yeah, heard of stacks and queues? Stack Overflow, maybe? I don't know. Yeah, like, okay. So stacks and queues are pretty, I would say they're easy data structures, but they're essential data structures, and they're exactly what you would think. So here I've just got, let's say, 4 elements in each of these, right? And this is the major difference between a stack and a queue. And with a stack, you can think of it like as a literal stack of things. The most common example you'll hear is like if you ever go to like a cafeteria where there are plates that are stacked in a thing, you pull one off the top, right? So with a stack, you're always pulling elements off the top. If you put like plates back on, you can only take the top one off still. With a queue, this is what we might refer to as a line in the United States commonly. But other places in the world, this is more intuitive because a queue is just an ordering of kind of like a first come, first serve. You know, you just wait in a line, wait for a resource in an ordered way. So the first one in is the first one out. So let's talk about it a little bit more. We'll start with a stack. And so both of these are just collections of elements. And so with a stack, the acronym is LIFO, which is last in, first out. And so if you're thinking about like that stack of plates, if you have a stack and you put something on top, you go to take something off the top, it's going to be the thing that you just put on top, right? It's not going to be the first thing. So if you put several, you put 1, 2, 3, you have to take 3, 2, 1 off to do that. So these are the basic operations. Really, these two are the major operations that define a stack. And so it's the push and pop. And they're exactly what they would sound like. So in the case of push, you're adding an element to the top of the stack, or the top of the collection. And in the case of pop, you are removing an element from the top of the collection. Now we usually have 2 convenience methods that are around, and those are called usually peak or maybe top in some cases. You'll see different words used. But all that does is let you look at that first element without removing it from the collection, which is convenient to do sometimes. And then, of course, usually you'll have a size indicator of how many elements are in a collection. So just walking through a stack, just to think about it, we'll start with, this is just an empty stack here. And our first operation, if we're going to push the element 1, and think of these elements just like our nodes in a linked list, right? 1 goes onto the stack, and so we want to push 2. 2 is going to go onto the stack. And if we were to call peak, then that would show us 2. And in our case, in C++, it'll give us a pointer to 2, so that we can look and see what's there. But it won't remove it from the collection. So then if we were to push 3, 1 up there, and then if we were to call pop, which one will we get back? 3, yeah. And then it's removed from that stack itself, and that goes back to 2 elements. So some applications of stacks. Kind of, I guess, a practical one is if you think about like a web browser, right? Like you click a link, you go to a page, you click a link, you go to the page, but then you can hit the back button and go back. So the way that that's usually implemented is a stack, and each time you click a link, it gets pushed onto the stack. And if you click back, it pops one off of the stack. So another way that stacks are used is pretty heavily in programming languages, in actual runtime of software, right? So if you can think about like, you've got like your main method, your main function, and you've got other functions throughout, right? So from main, you might call a function, and what will happen is kind of all of the variables that are in scope within that function you're in right now get pushed onto a stack. Then you go to the next function, which could call another function, right? It could keep going on, and it would just keep pushing on the stack. So you'd be pushing more and more things, and then once those functions start to return, you pop from that stack. And so you're just pushing down as you execute and then popping as you return. So that's pretty common in order to just store context. So thinking about implementing a stack, there are, as many ways as you want to implement the stack, right? Because the only kind of principle is that when you put something in, the last in is the first out, right? And so however you want to do that, you can do it. Obviously, there are some pretty intuitive ways to do it that are kind of the most efficient ways to do it. So one that you can do, if you have just an array, right, just a chunk of memory, you can simply store the elements in the array and just keep track of where your top of the stack is, right? And so because of the way that you add and remove, you'll add, and you only have to add this way and remove this way, which is very nice. So the only problem you could get into in this scenario is that you would run out of memory, out of space, in which case you would just need to double the size of your array, copy it over, kind of like we've talked about with implementing a linked list if you were to do that with an array. So if you want to use a linked structure, like a linked list for this, it's kind of the same thing. You can imagine we don't need doubly linked, we just need singly linked. So in this case, I'm storing it with just a pointer to the next and a pointer to the top element, right? And so then you can imagine when you pop this element off, you just change top to now point to this element. And you can just continue to do that as you go. So when we think about kind of the trade-offs of how this is implemented, you can think about, so with like the contiguous structures like arrays and just like a chunk of memory, this still works, it works well for everything except for if you run out of that allocated space, then you've got to do that resize operation. It's a little bit expensive. But in terms of the time needed to add an element or remove an element, it's just a constant time, right? It doesn't depend on the size, it doesn't depend on how many elements are there, because you've always got a pointer or an index directly to that element that's on the top. So in a similar way, when we look at doing this like with a linked structure, we just have a singly linked list, and each element points to the next element, and then the list itself has a pointer to that top element, right? And so we can just add to the beginning, and we can remove from the beginning of the list, and it's still a constant operation, right? Because we're just changing those pointers around. And we do have the benefit of not needing to resize, that whole chunk of memory if we run out of space, because we're doing that for each node. On the other hand, we do have to store an extra pointer for each node, so there's a little bit of a trade-off there. But generally, either way of implementing this works well. Before I move to keys, are there questions about stacks? It was kind of a fast introduction, but they really are pretty simple. And we'll look at code for implementing them, but honestly, if you've looked at the linked list code and gone through that, it's really just a simplified version of the linked list because you don't need as many features in order to implement the stack. So we'll move on to a queue. So a queue, also a collection of elements, right? But this time we're going to use the FIFO acronym, first in, first out, which is exactly how a queue works in real life for anything. So we have some basic operations. In this case, we'll call them enqueue and dequeue. So enqueue being to add an element to the collection at the end of the line, at the end of the queue, and dequeue being to remove the element that's at the front or the beginning of the queue. And just like with the stack, we usually have these other two functions around for convenience. One letting us just kind of look at the front of the queue to see what's there without removing it, and another to let us see how many elements are in the queue overall. So let's kind of just step through a queue, and I don't know, for some reason a queue is horizontal, stack is vertical. But let's start with the empty queue. And if we enqueue an element with 1, just goes down into the queue. We enqueue 2, into the queue. And you can see here I'm doing this kind of the opposite of how we would do it in an actual array. Because if we were to take an actual array and to do it this way, like if this were index 0, 1, 2, right, we're shifting every time, which is not great. But this is kind of just for the convenience of visualizing it. So we've got 2 elements in. Now if we were to call peek on this queue, then we would get back a pointer to 1, which is at the front of the queue. And then if we enqueue another one, 3. And then if we were to call dequeue, which one we get back? 1. Yeah, so the opposite of the stack, right? And then the queue has 1 less in it. So thinking about applications of queues, that's also kind of limitless here. So you can think about any general waiting task or scheduling task where you're waiting for a resource that's constrained. This can be used like a print queue is a good example. CPU scheduling for processes, but we'll talk later in the semester about a priority queue, which is a lot more interesting. So it's not just a single, who's ever first is the first one to go. You can have priorities to give things, jump ahead of other things, which turns out to be fairly important in a lot of computing tasks. So you can think about some practical queues, if you're waiting for a parking permit, right? You sign up and you're on the list, and then it just goes down the list as whoever was first is the first one to get one. Within other algorithms, so both stacks and queues obviously used in other algorithms. So search algorithms in particular, like breadth first search, will make use of a queue as it does that. So thinking about implementing a queue, again, you can kind of take 2 approaches here. I mean, you can really take as many as you want as long as you follow the principle of the queue. But the ones that are most efficient, you could use this contiguous structure like an array or a vector. But you need to keep track of the first element and the last element. And so what that will do, if you imagine, like here we've got ABC, right? And the beginning is A, so that's the first one that went in. Whenever we dequeue that, right, this spot is no longer used, and first moves here. So now we've got an array that's kind of got these offsets, and really the best way to think about it is a circle. So essentially have the end connect to the beginning, and that way you've always got just pointers around the circle. And again, the only thing you have to worry about here is if you run out of space, you do have to reallocate, usually double the space so that you can continue to add elements to the queue. With linked lists, or with the link structure, we kind of do the same thing that we've been doing. In this case, we'll have a pointer to the beginning and the end. We only need the single link there because we'll only be taking from the beginning and adding to the end. And so for both of these, adding and removing is a constant time operation. So it doesn't matter how many elements are in either of these queues. The only thing to that being if you do have to reallocate space, then yeah, it does matter how big it is. But in general, both approaches, in terms of the operations, are constant time. So thinking about the queue implementation and approaches to doing that, with an array or a vector, we just need to track the beginning and the end index of that array. We need to add at the end of the array, but we need to think about once we get to the end of our actual indexed array, we have to just do a little bit of math and start back over at the beginning to make it kind of a circular array, and just keeping track of that beginning and end point in the array. If we're using a linked list structure, it's a little bit easier. So you just have each element with a pointer to the next element, and then the list itself has a pointer to the beginning and end of the queue that you've got. And so you can add to the beginning, and you can remove from the end of that structure. So in terms of implementing this, we can kind of simplify. We have our node structure that we used in linked list, if you remember, and I'll show you what exactly that looks like. So when we were doing this with linked list, we just had our node, and we had a next and a previous pointer so that we could go both ways in the list. In the case of doing like a stack or a queue, we don't need both of those. We can just be satisfied with the next pointer. And so when we look at kind of the headers for like a stack, right, it can be very basic. We'll just have a push operation to push our data, have a pop operation to remove one, and a peek to look without removing. So something to think about as you implement this is there is a choice to be made in C++ especially. Think about this pop operation here, right? What if the stack is empty? What should that return?
False.
False. So it's an integer right now, right? Like so they were storing integers.
So 0.
But what if 0 is the element?
It would return null.
But can it return null if it's an integer return? So what you could do, there's two different approaches here, right? So the problem is that it's got to return an integer, but we wouldn't know. Like we could pick an integer and say, okay, that's the one that means it's empty, but then we wouldn't be able to store that integer ever in our stack. So rather than returning an integer, we could return a node, a pointer to a node. In that case, we could always return null, right? And then you would know there's nothing there. Or what we could do is rather than return an integer, we could return a Boolean value, a true or false, and we could pass in a parameter, a reference, where it would put the value, which is a little bit, I don't know, non-intuitive. I think if you come from other languages, some of the ones that are after C++, like the Python, Java, C#, that kind of world, passing in a reference where it's going to store a value coming back to you, it just gets a little bit messy, but it's perfectly fine to do. And so you'll see in the code that you use, so you'll have a challenge that's related to stacks and queues, but it's challenge 2, I guess. So it will be like a month from now before you ever see that, and you'll have forgotten all of this. But when you start remembering it again, you'll see that the code that the base code given to you uses a Boolean and passes in a reference for that. There is another option. Anybody think of another thing you could do if pop was called and there was nothing in there?
Make it void.
You could make it void, but I don't know, how would you indicate to the caller that there was nothing in there?
Can void not return anything?
Yeah, it won't return anything. But what if there is something in there in that case then?
I mean, you could just include that as in part of whatever the void function is. It'd be really dumb, but it would work.
Yeah, like you could pass in other things, right, and store there. So if you're, if anyone comes from a world of like, I don't know, like Java probably is the most common, you can always throw an exception, right? So, all those wonderful try-catch blocks that you see. Same thing, I mean, every language supports it. C++ supports that. So rather than worrying about, like, you could always have your return be the value, but if it was empty and somebody called it, you would throw an exception that says, hey, it's empty. And in that case, whoever's calling it would have to always, catch that exception. So that's another approach. And these are all just kind of language-specific things, right? And style-specific. So kind of whatever you choose as the easiest or whatever makes the most sense here. But the important point being that this is kind of a detail that can go overlooked, and you might not notice it because the condition may never come up in testing if you're using some obscure value as like there's nothing in here kind of thing. And then one day it happens and everything breaks. And so that's the same thing for like peak or anything that's going to tell you the value that's in here. That's something that you've got to think about. So looking at the queue class, again, very basic, just like the stack, but we keep track of the beginning and the end here, and we have these same methods, push and pop, and peak. So when I was explaining queue earlier, I used enqueue and dequeue. You will see the words push and pop used for a queue and a stack. So I believe in C++, one of the standards, when they standardize this, pop and push are used for both queues and stacks. So it's something to be aware of. Typically, like when we think about a queue, we think about enqueuing something and dequeuing something, but you can alias that to push. So push is enqueuing. Yes?
Why do we need to return an integer with pop function?
With pop, so in this case, the queue is a queue of integers. And so when you pop something from the queue, you want to return that element.
So it would not return the queue after the element has been popped?
So no, not in this design. No, you could design it that way if that was more convenient for you. Yeah. So yeah, the way that this is structured, typically, it will return the element that is in this case, the front of the queue or the top of the stack, whichever, and then this class will maintain the structure still. And so yeah, it'll remove that element from its own references and hand it off to whoever called it. But yeah, I mean, it's a good question because, again, these are all just design choices, right? And so like the ones that we look at here, these are kind of the ones that have stuck, right? Like that most people have used, that have put in the standard libraries and stuff, but that doesn't mean you couldn't do it a different way. And it's just a matter of these principles of, the queue is the first in, first out, and the stack is the last in, first out. All right. I think that is all I want to cover today for you guys. Do you have any questions since we have a little bit of extra time? Is everybody feeling okay? I would encourage you to look at the linked list code if you get a chance. So next week on Monday, we'll talk about time complexity. And then Wednesday, we will do an exam review. And then Friday, we will do an exam. So if you get a chance to look at linked list before that exam review and have questions and stuff, that would be great. That'll be the major portion of the exam, as you might imagine, because that's what we spent the most time on. But other than that, have a great weekend. I will see you on Monday.